All right, so we're kind of moving forward with our discussion on compound interest right now. We talked about compound interest and did an example at the end of the last video. And now what we want to do is move into this concept of what's called continuously compounded interest. So before we can really get into that, we have to do a little bit of groundwork. Let's suppose for a second that we have an account that we make a one-time investment in, and we're going to make some very unrealistic a very unrealistic assumption about this account. We're going to assume that it has an interest rate of 100%. Obviously, that's not something you encounter when you're making investments, but this is going to serve a purpose, and you'll see where this is going soon. So in that case, R is equal to 1. That would be the numerical representation of 100%. Let's suppose also that our initial deposit is just $1. And let's suppose also that we choose to wait only 1 year before seeing how much interest we've accumulated. So now we're not going to make any assumptions about how many times interest is compounded per year. We're just going to say it's compounded n times. Plugging this information into the formula that we came up with for compound interest would give us this expression right here. Notice n is the only unknown still. But there's your rate of 1. We multiplied n by 1 for the 1 year. The principal is 1, so it's like I have a 1 out here that you're not seeing that's being multiplied. This is kind of putting this in a simpler form. Now what I want to do is first note that this value, this account balance at the end of that first year, depends on what n is equal to. So for different compounding or different choices of how frequently we compound interest, this will give us different values. And specifically what I'd like to see is what happens if we let n get bigger and bigger and bigger without any kind of bound. So that's what this table down here is doing. If I plug a 1 in for n, I get 1 plus 1, which is 2, obviously, to the power of 1, which is still 2. So plugging a 1 in for n gives me an account balance of $2. It doubles my money in 1 year. So that's great. That's also what you would expect if your annual interest rate is 100% and you compound it at one time. If we plug a 2 in for n, and I would have used a calculator for this, you get 2.25. So you get more money by increasing the number of compounding intervals. And that conforms to our intuition. That's kind of what we expect to happen. In fact, as n gets bigger and bigger, this value is also getting bigger and bigger, but it's tapering off at the same time. So you notice we go from 2 to 2.5 here. When I double n here and go, use 4, so this is like quarterly compounded interest, I get 2.441406. Obviously, if we're looking for actual dollar amounts, I would have rounded this to 2 decimal places, but I want to see what's happening, further out here. So as n gets bigger and bigger, notice we eventually plug in a really large number, 1,000,000. So interest is compounded 1,000,000 times per year. That's multiple times per day, many, many times per day. The number that we get here is not significantly larger than the ones that come before it. So what this is suggesting is that if n is allowed to just increase indefinitely, this number will not just shoot off to infinity. It seems to be leveling out somewhere. And that is where we get this concept, or the concept of a number that we call E, lowercase e, also known as Euler's number. That's what the E is standing for there. And E is approximately equal to this, 2.718281828846. I say approximately because this is rounded. E is an irrational number, which means it has infinitely many digits after the decimal point, and there's no repeating pattern to that. But if I round it here, this is what this would come out to. And you can see, this number, it has less decimal or less digits after its decimal point, but this is like this after rounding a little more. So the concept of allowing n to increase indefinitely is wrapped up in something that we talk about in the first chapter of our book called limits. So we need to talk about this formally, we need to be able to deal with limits. We haven't talked about limits yet, so I can't make this too formal quite yet. But we have enough information here. So this E is a really, really important in mathematics. In fact, a really important number in mathematics. In fact, it's considered to be one of the most important numbers in math because it shows up in all sorts of different places. It's an incredibly useful number, despite being, irrational. Now, where does this topic fit in to the concept of compound interest? Because we kind of created a contrived and really unrealistic account from which we derived this number. So it doesn't seem like that would show up, in practice. But here's how it shows up in practice. Let's suppose that we're dealing with the general, formula or the function for finding compound interest. Now, what I'm going to do is something that we do a lot in calculus called a variable substitution. What I'm going to do is take some of the stuff that's appearing in this expression and define a brand new variable that involves some of that stuff. Specifically, I'm going to call this new variable m, but I'm setting it equal to n over r. That's how I'm defining it, okay? Now, if you notice in parentheses here, I have r over n, which is the reciprocal of this. So this fraction here can be written as the reciprocal of m by making a substitution, which would just look like 1 over m. Similarly, I can make a substitution up in this exponent as well. If I were to solve this thing for n, then I would get n equals mr. And I can use that mr as a replacement or a substitution for the n here, which gives me mrt. That t is just along for the ride there, okay? Next thing I can do, I can use an exponent property which says that this is actually just equal to this. Notice I have p times in square brackets 1 plus 1 over m, all to the power of m, and then that is all raised to the power of rt. Remember, when you raise an exponent to a power to another power, you can multiply those exponents together, which would give me this. Now, the reason I did all that is because if you specifically focus on what's happening in the square brackets here, we have that exact expression that we saw right up here, only I'm using an m instead of an n. And we just learned something about this expression. We learned that if n gets arbitrarily large, this whole thing turns into this number e, right? Well, if we let n, and n, not m, but if we let n get arbitrarily large, how do we interpret that here? Well, n represents the number of compounding intervals per year. So if I'm letting n get bigger and bigger and bigger, that means I'm compounding interest more and more frequently over the course of the year. And if we think of n as going off towards infinity, then what that turns into is compounding interest at every single instant in time. So that's where we get this idea of continuously compounded interest. But if n gets arbitrarily large, then the same thing happens to m. Notice r is a constant, this denominator. So if n is getting bigger, I'm allowing my numerator in this fraction to get larger and larger and larger, which makes the whole fraction larger and larger and larger, which means m is getting larger and larger and larger. As n shoots off towards infinity, m does the same thing, which means this thing in here in the square brackets is doing exactly what happened here. It's turning into e. So this turns into, drum roll please, PE to the RT. A simpler looking function, but what it represents is the account balance after T years with a principal of P of an account that continuously compounds interest. It compounds at every instant in time. So this is a fairly easy formula to use, and we're going to do an example where we use it. So let's come down here. Suppose you make a one-time deposit of $5,000 in an account that accumulates an interest at an annual rate of 7.3%. If interest is compounded continuously, determine the account balance after 12 years. So we're using this formula right here. 12 is the number of years. So in fact, actually, before I get that, let's get all the information down. We need P, we need R, we need T. E is a number, it's a constant. There's nothing to plug in for E, okay? So P is my initial investment, my principal, 5,000. What is R? Well, R is the interest rate, but as a decimal, 0.073. And then T is the number of years. T is 12. So we're computing A of 12, the account balance after 12 years. According to this formula, it's P, which is 5,000, times e to the power of RT, 0.073 times 12. This goes into a calculator. Don't do this by hand. You need a calculator specifically because e is an irrational number. It's really hard to do manual calculations with it. But your button should have a calculator in there that looks something like this. If it's a scientific calculator, a button that shows e to the x. This is a thing that you can press, and whatever you type in after that, again, if this is a scientific calculator, will take e and raise it to that power. So you'd want to put this product in for that x there. Your calculator knows what to do with that. I plugged this into a calculator ahead of time, and I got a number that was approximately 12,006.38, which, remember, we interpret that as $12,006.38. Okay? We have more than doubled our money over the course of those 12 years. So that's continuously compounded interest. All right, we are shifting gears now. If you looked at the title of this section, it's a review of exponential and logarithmic functions. We've been dealing only with the exponential part of that. So now it's time to move into logarithms. But before we can get into logarithms, a little bit of review on inverse functions is worth doing. So here we have a graph of the function f of x equals x cubed. This is not an exponential function. Even though it has an exponent, it's not an exponential function because the exponent is a constant. Exponential functions have a constant in the base and a variable in the exponent. This is what we call a power function. Now, this graph has some important properties to it, but I just wanted to show it to you there. Let's move on to here. So here's where I talk about the main property that we're after. The function f of x equals x cubed has a property called 1-to-1. And what 1-to-1 means is that if you look at any number in the range of that function, any output that you can get from that function, then there's only ever going to be one, or exactly one, value in the domain of that function that when you plug it in gives you that value. So here's kind of an example of what I mean. If we look here, pick a y value. Maybe this one right here. I don't know exactly what that is. It looks like it's a 3, right? If I look on my graph here, only one point on the entire graph of this function has 3 as that y value, because all the other points are higher or lower than that point. So if I were to find that y value, 3, and figure out what value of x did I plug in to get that, there's only one value of x that does that, whatever this number is here. It's the cube root of 3 technically, but I don't know what that is as a decimal off the top of my head. So only one value of x can be plugged in to get me to that specific y value, and that's true of all of the outputs of our function. So that's what makes this thing 1-to-1. 1-to-1 functions you can always identify from their graphs because they pass something called the horizontal line test. If I take a horizontal line and put it through this graph at any point, it will always only ever intersect that graph at one point. And that graphically is just an illustration of what we just talked about, this one input for any one output thing. An example of a function that is not 1-to-1 is the function y equals x squared. That gives me a parabola, and if you notice, I can put a vertical line through that parabola that hits it in 2 spots, there and there. And what that means is that both of these points have the same y value, whatever that y is right there, but 2 different x values. One there and one there. So 2 different inputs give me the same output, which is not what happens with 1-to-1 functions. Why are we talking about 1-to-1 functions? Well, 1-to-1 functions have something really useful. They have something called an inverse, or an inverse function. And basically, an inverse is a function that relates to your original function f of x in this way. if you do function composition with them, so f inverse is the notation that we use. With -1 exponent does not mean 1 over f. It's just we borrow that notation to mean the inverse of f. But f inverse of f of x is equal to x, whatever the input was. So in other words, the inverse undoes whatever f did to x and gets us right back to our original input again. Or in other words, you can use inverse functions to solve things like this for x. It works the other way around too. F of f inverse of y is equal to y. So the f and the f inverse canceled each other, and the y is what's left. Okay? So you are used to thinking of inverse functions because, again, all of the stuff we do in this video is review. One way of thinking about them graphically is if you have the graph of f of x. So down here we have the graph of y equals x cubed. Again, you can see it labeled here. For any point that appears on this graph, suppose this is the point AB right here, then the inverse of this function, which is its own function, will have the same point but with the coordinates swapped. So instead of AB being on the graph of that function, it's going to have BA. And those 2 points are reflections of each other across this line y equals x. So if you know what the graph of f of x looks like, you can reflect it across the line y equals x, this green dashed line, and the result of that will be the graph of your inverse function, this blue one in this case. The inverse of x cubed is the cube root of x. And that's easy to see because if I have my original function x cubed, but then I take the cube root of that, that's like f inverse of f of x. That's basically what you're seeing, but we know that these things cancel out and just leave me with x. So the inverse undid what f did to x. Okay? Now that we've gone through that little bit of groundwork, we can talk about the logarithm. So a logarithm is just an inverse of an exponential function. If we go back, let's see if I can find it. If we go back to the I think second page of these lecture notes, we showed a graph of one of the exponential functions right here, 2 to the x. Notice that it's a 1-to-1 function. Any horizontal line I put through it will only intersect that graph at one point, which means this thing has an inverse. Its inverse is called a logarithm. Specifically, if we have a function y equals b to the x, then the inverse of that is called the logarithm with the base b of x. Notice the base here is the same as the one used here. Okay? Usually we just read this as log base b of x. Okay? So, a little bit of terminology to talk about. The subscript b that we just talked about is called the base of the logarithm. So it's the same terminology that we use for exponential functions. The x that was plugged in, that log base b of x, is called the argument of that logarithm. So that's the term that we use for that. And here's the relationship between these two functions. If b to the power of x is equal to some number y, then the log base b of y is equal to x. So in other words, x is the exponent, y is the power. When I take the logarithm of that power, it leaves me with that exponent. So it tells me what that exponent is when I evaluate. Okay? A couple of other notational things. If there's no base written there, so if you just see log, which notice one of our examples down here just has log, there's no base written, then you assume that the log has a base of 10. If we use this notation, ln, instead of log for log, then what this is it's the log where the base is e, that number that we just talked about. We call this the natural logarithm, and it's the most frequently occurring logarithm in mathematics. It shows up all the time because e shows up the most frequently when we talk about exponential functions. Quick aside, in some courses, usually like some engineering or physics courses, there is a convention of when you write log this way, instead of meaning base 10, they mean the natural logarithm. We don't use that convention in this class, but just in case you come across that at some point in your mathematical journey, that is a thing that sometimes happens and it gets confusing for people. So I'm just mentioning that here. Okay. let's go through this example here, and then I'm going to stop this video and we'll wrap things up in the next one. So here I want to evaluate a few different logarithms. Okay, so for part A, we're asked to evaluate log base 2 of 32. Now, you can use calculators and things to solve these. In fact, one of these problems will require a calculator, but the rest of them actually don't. So what I'm going to do is rewrite this logarithm, but in exponential form. That means taking it from this form and rewriting it in this form. So the base is 2. The exponent, x, is the thing I'm trying to find. I don't know it yet, so I'm going to call it x. The y, the thing that's showing up in this logarithm, is what the result of this exponential should be. This should equal 32. Okay, so now I'm looking at this and I'm thinking, what power can I raise 2 to make 32? And I actually can figure that out pretty easily. 2 to the 5th power equals 32. That's an easy one to verify. So what that means is that log base 2 of 32 equals 5. And that's kind of how you approach this, you know? So like part B, let's look at part B. I wanted to find log base 27 of 1/3. So this is saying 27 to what power is equal to 1/3. This one's a little bit trickier, but I'm noticing that instead of getting like an integer as a result here, I'm getting a fraction. 1 over something. That makes me think of reciprocals. And I know that if I raise an integer or a number to a negative power, the result is the reciprocal of something. So I'm expecting my x to be a negative number. Next up, if the negative is accounting for this reciprocal, let's just focus on the 3 here for a second. What power can I raise 27 to make 3? Well, if I raise 27 to a positive integer power, I'm going to get a number that's greater than or equal to 27. Because, for example, if I do 27 squared, that's 27 times 27, which is much bigger than 27. If I'm trying to get to something smaller like 3, that suggests that this is not an integer power. In fact, it's a radical. If you think about it for a second, you might come to the conclusion that if you take the cube root of 27, you get 3. But taking the cube root of something is the same thing as raising it to the 1/3 power. So putting this information together, that exponent must be negative 1/3. So now I know that the log base 27 of 1/3 is negative 1/3. Cool. All right, so we're seeing that logs can give us positive numbers. They can also give us negative numbers. Exponential functions can't do that. Exponential functions only ever give us positive numbers. So this is right away we're seeing a difference between what logs can do and what exponential functions can do. Part C will also kind of have that same thing going on. So here we're looking for log base 12 of negative 4. Putting this in exponential form again, 12 to what power equals negative 4? That's the question we're answering by solving this logarithm. However, as we kind of just mentioned, exponential functions can't give you negative numbers. There is no value of x that would ever make this true. No real number anyways. So this has no solution, which means this logarithm is undefined. Log base 12 of negative 4 is undefined. Now, there's nothing special about negative 4. Any negative number here would have created the same issue. In fact, 0 would have also created the same issue. So what this tells me is that when I take a logarithm of really any base, there's also nothing special about the 12 here, I can't plug in 0 or negative numbers. I'll always get something that's undefined. Let's move on to D. Log of 100,000. Remember, if there's no subscript there, we assume that the base is 10. So this is saying 10 to what power is 100,000. Now this one is very, very easy because there is a nice trick to figuring out powers of 10. You just count the zeros. I see 5 zeros here, so that means that this is equal to 10 to the 5th power. X is 5, we get the same answer as part A. that means that log of 100,000 is equal to 5. E. And it is coincidence that part E is the one that has a logarithm whose base is also E. I didn't plan that, but that's kind of cool. So for this, ln of 2, normally if we're following this pattern, we would say e to what power is equal to 2. The problem with trying to do that one mentally is that e is an irrational number, and we're raising it to a power that's giving us an integer. You're not going to be able to pull that one off mentally. You might be able to approximate it. So for one thing, I could tell you for sure that this number is going to be less than 1, because remember, e was approximately 2.71, and I'm raising it to a power that's giving me something smaller than that base. As we saw up here, that implies that we're looking at a fraction, something that's less than 1. In fact, I shouldn't even use the word fraction, because it may not be rational at all. In this case, it's not. So for this, I'm not going to get anywhere using this approach. So I'm going to say, let's try something different. For this, all I do is I plug my number right into my calculator. So your calculator is going to do the work on this one. It's an infinite non-repeating decimal because this is an irrational number. 0.6931 is what we get if we round to the 4th decimal place here. But it does have an infinitely a non-terminating decimal. Okay? So on your calculator, you should see a button that looks something like this, ln. It might have an ln of x there, and you use it the same way you use the e to the x button. If it's a scientific calculator, plug the number in that you're trying to find the natural log of. So you'd put a 2 in there, and then hit this key, and it'll give you this answer. Okay, so nothing really to do on that one. Last one, log with a base of 0.5 of 1. Logarithms can have a base that's not an integer. We already know that from our natural log, but here's like a fraction, 0.5 or 1/2. So this means 1 to what power is equal to 0. Oh, I'm sorry, I mixed that up. 0.5 to what power is equal to 1. Well, in this case, there's nothing special about the 0.5. We know that if you take any positive number and you raise it to the power of 0, you always get 1. So regardless of what this base is, as long as it's positive, x is automatically 0. And that's a really important thing to remember. So log of any base of 1 is always equal to 0. Nothing special about the 0.5 there. Okay? All right, let's stop this video here. We'll kind of continue on in the next one.